Okay. Since there's discussion right after this, I will not ask you for questions right now, and I'll just jump into it. But if there's questions as we go along, feel free to stop me. And I'll say, no, I won't answer it. I'll do it during discussion. No, that's not. I will answer them as best I can. So I have an ambitious plan for this third and last lecture on flavor. I want to first finish the discussion on mixing, because I want to talk a little bit about BB bar mixing. And hopefully I can do that in some 30 minutes or so. And then I want to spend the last bit of time we have talking about effective field theory. And so we'll see how much we can actually do. And so if you have my notes, I'm not going to be covering everything in those notes. Good reading for later. So the first thing I want to do, I want to discuss time evolution. Time evolution in mixing. So mixing is a dynamical phenomenon where a particle turns into an antiparticle back and forth. But we've talked about quantities that don't show this explicitly, really kind of average quantities where you can see the effects, but kind of indirectly. So in order to understand time evolution, all we need to do is solve Schrödinger equation. And it's a fairly simple equation because it's a 2x2 system. Oh, this is all wet, sorry. So now I'm not going to call it K0, K0 bar. I'm going to call it X0, X0 bar because X can stand for kaons, B mesons, D mesons, B sub S, whatnot. And the equation we want to solve is Schrödinger's equation, where the state is K0, K0 bar, but we can actually just go to the eigenstate. I'm just going to call it X, I guess. And in the kaon system, we've seen there's a short-lived state and a long-lived state. For the B system and the D system, the lifetimes are almost identical. So we adopt a different notation where we call one state the heavy one and the light one, although they're almost degenerate. So the masses are nearly equal, but the time lives are almost identical too. And well, the eigenvalues we already defined as MHL. Well, we could call them short and long. So that's nice because it's diagonalized already, and every child in kindergarten can actually solve this equation. Okay, primary school. And of course, all you get is just the exponential. H of L T times e to the minus gamma t over 2. So this is great. This is what eigenstates do, and it doesn't look very exciting. But when you actually do an experiment, you typically don't produce a state which is one of these eigenstates because the interactions that produce them are usually weak interactions that involve, for example, some W boson. And you tend to produce, say, a B quark or an anti-B quark, but not a linear combination of them. Because, for example, you have a W plus, not a W minus in the transition. So what you tend to produce is really the states that we call X0 or X0 bar. And those are not eigenstates of the Hamiltonian, so they actually evolve in a way that in a way that mixes the states with each other. And it's actually not very easy to describe what happens. So what I'm going to do is I'm just going to rewrite those states in terms of the states that are already diagonalized and evolve simply. And that will tell me how these guys evolve. And now when these guys decay, these diagonalized states, the heavy and light, the eigenstates, they also decay via weak interactions. So it's useful to think of them as being part x0 bar, because if the x0 decays into pi plus, then the x0 bar decays into pi minus in semi-leptonic decays, for example. So you can tell which one is which. So how am I going to do this? Well, at first I need to write these original states, x0, hl, in terms of, or x0, say this states x0 in terms of the eigenstates. And, well, let me do something first, because I'm changing notation. Remember yesterday we defined the eigenstates in terms of the flavor states introducing epsilon. There was a 1 plus epsilon k0 and a 1 minus epsilon k0 bar. It's kind of standard notation, and I warned you yesterday that we would change notation to use, instead of 1 plus epsilon and 1 minus epsilon, these parameters called q, p, and q. And the h and l just correspond to a plus and a minus sign. So p is basically what 1 plus epsilon used to be, or 1 plus epsilon over this normalization factor of square root of 2 something. And q would be the 1 minus epsilon. And it's just a different notation. And in terms of that notation, we can solve this and write x0 as 1 over 2p xh plus xl. And x0 bar is the same thing, but in terms of q here, 1 over 2q xh minus xl. So now it's very simple to remember. What I want to do is I want to find out how x0 evolves in time. So I have to imagine that I produce an x0, but it's really not an x0. It's a linear combination of these two guys. These two guys evolved in a very simple way in time. And then at the end of the day, I want to rewrite that in terms of x0 and x0 bar, because those are the guys that are going to decay anyway. So it's a simple exercise. Let's do part of it so we can see how it goes. For example, I can write x0 as 1 over 2p x heavy plus x light, but x heavy of time is given by e to the minus I m heavy e to the minus gamma heavy t over 2 x heavy of time 0 plus the same thing with light. And now I can write these two guys, x heavy at time 0 and x light at time 0, in terms of x0s. So actually, let me not do that because it takes more time. But this guy can then be written as px0 plus q x0. And of course, the bottom one with a minus sign. And when I write it this way, just x0 bar. Without a time reference, I'm always meaning 0 time. That's the original state. So let's put it all together. So I expand it this way, and I'm going to combine the terms with an x0 and combine the terms with an x0 bar. And so I get finally x0 of t is equal to, well, some function, which I'm going to call f plus of time, times the original x0, plus a function times q over p, f minus of time, times x0 bar. And x0 bar of t is going to be just p over q minus t x0 plus f plus of t x0 bar. And these functions, f plus and f minus, are given, of course, just in terms of these exponential factors. And it's just a question of combining, say, the sum of those terms or the difference of those terms. So for example, F plus is the sum of these two factors. And it's kind of useful to write that by factoring out the average masses and the average widths, which were our M and gamma in the 2 by 2 matrix that we introduced yesterday. So let me write that way. You can write this as 1/2. Actually, I'm going to write it this way just to get the full. You can write it either way, but just to give you an idea of what I want to do. Minus gamma heavy T. And then if I do it that way, there's a 1 here. 1 plus minus e to the I delta M, right? Yeah. Delta MT e to the Q. How's the delta gamma T over 2? And if you want to know what you get for the minus case, just put a minus. Oh, I put it there already. So that's the whole thing. It describes the time evolution of the states. And some things here worked out very nicely. For example, at time 0, you see that F plus of 0 is 1 and F minus of 0 is 0, which is what I wanted to do because I wanted to start with the x0 state. You can do the opposite situation if you want. So x0 of time 0 is pure x0, and x0 bar of time 0 is pure F minus. It's pure x0 bar, sorry. I had too much ice cream. Okay. So, and there's one interesting thing that I'm going to use. I mean, in a lot of the formulas that we'll write down, we're not going to write that many, for BB-bar mixing or time evolution in mixing of these states, we could just keep F plus and F minus implicitly, and then at the end of the day, you can put it into mathematics and make plots and see what happens. But it's kind of nice to do things analytically, and I'm going to show you later that for the B system, delta gamma is much smaller than gamma. And so we'll see that coming out later. But if delta gamma is much smaller than gamma, it kind of makes sense to just neglect delta gamma. So if you neglect delta gamma in these expressions, then something kind of nice happens because you get cosine and sine here. So you can do the algebra for F plus of t, well, F plus and minus become e to the minus I. Now I'm going to have the average mass, which I should have done to begin with. I have to take half of this out to make it into a cosine. So mh plus that half is just the average mass. So e to the minus imt, e to the minus gamma t. I'm missing the 2 here, right? And then for the plus sign, you just get cosine of 1/2 delta m over t, delta m times t. And for the other case, you get I think it's minus I times the sine of delta mt. So that's going to come out handy. Okay. So that's a little formalism. Now let's actually get into some actual physics. This is going to be kind of nice, and in that we'll be able to relate to some experiments that are now very famous. So what I want to do is look at asymmetries. CP asymmetries, and we talked about CP asymmetries yesterday. I actually wrote one, this delta asymmetry, and of course epsilon was a measure of that. The delta asymmetry was the difference. In general, we're going to have asymmetries, which are just the difference of some, some process, the rate at some process, the rate at which some process proceeds. Take away the rate at which its CP conjugate proceeds. And to make it an asymmetry, to normalize it to 1, you can divide by the sum of these things. So gamma of the process divided by gamma of the antiprocess, where the bar just means CP conjugate. And I want to make a kind of a very simple general statement. These widths are always of the form, some factors that are common to everything, times the matrix element square of some amplitude. And let me imagine that I take the amplitude, and there's a CP even part to it and a CP odd part to it. So let me call that amplitude A plus A minus, where plus means that it is CP even and minus that is CP odd. And then let me take away from that the CP conjugate. And imagine that you divide by the sum. And what you see right away is that this numerator, the magnitude squares of plus and minus are going to cancel, and the only thing that contributes is the cross product. There's a twice, actually 4 times the real part of A plus times A minus star divided by some positive stuff. And the lesson I want to draw from this very simple observation is that in order to have CP asymmetries, you have to have interference between 2 different amplitudes, a CP even one and a CP odd one. So there's many ways to get such interferences, but one that is particularly interesting is an interference that occurs when you have mixing. So suppose that you have a B0 state, and now we're really going to call it B0 because that's where the experiments are done for this type of mix of CP asymmetry. And after time, you can find it to be in a B0 state, or perhaps in a B0 bar state, and the probability for that would be given by the square of these coefficients here, right? The magnitude square. But now imagine that these objects can both decay to the same state, some final state F. The total rate for the B0 to go into this final state F will be made up of 2 pieces, one which corresponds to kind of the direct decay of the B0 into an F, and the other one which corresponds to having the B0 first oscillate into B0 bar, and then the B0 bar decay into F. And those 2 different amplitudes can have different CP properties, and you can have an interference between them. That's the idea. And I wanted to draw this graph because if you go to a flavor physics talk, you're always going to see this. I don't know why. But it's a simple idea. And it's actually very easy to compute. Right? All we need to do to compute this thing is to kind of do this thing, do the computation that I just outlined here, using for gamma of the process, the matrix element for one of these states to go into a final state. So I could write, for example, that the width for B0 to go into F at time t is equal to, and then I'm gonna break this into pieces as indicated here. So there's an F plus of t. Then there's sorry about this final state F, looks like the same function F, but let me call it final state psi. How about that? Some Hamiltonian, and then there's of course the original state B0, and then I have to add to that Q over P, F minus of t, and then psi H B0 bar. And of course there's some prefactor here which has to do with phase space and whatnot, and I don't care about it because it's going to cancel out in the ratio. Right. Okay, so what do we do with this? Well, I'm going to first of all make notation a bit simpler. I'm going to call this F plus A1 plus Q over P F minus A1 bar. And so the 1 here, the 1, refers to the final state. So 2 later on will refer to psi bar, the CP conjugate of psi. And the bar here tells you this was a B0 bar amplitude, as opposed to the absence of a bar here refers to B0. So this amplitude here, B0 to psi, is A1. B0 bar to psi is A1 bar. And then B0 going to the CP conjugate of psi will be A2, and so on. Okay? So now I can actually just compute this, and I'm not going to write it all out. I can take this, the square of this combination that I wrote here, and subtract from that the square of the combination that you get from a B0 bar of T going to psi bar, which would be the CP conjugate. And you get this humongous mess. And I'm going to make a couple of simplifying assumptions to give you an answer that's a little bit more easily written down. Well, first of all, I'm going to assume that A1 magnitude is A2 bar magnitude, and that A1 bar magnitude is A2. Now, this assumption we'll see actually is a very good approximation in many cases. I'm going to do something explicit for you to show you that. It also would be true if, and this is actually also easy to prove, if the final state is an eigenstate of the strong interaction Hamiltonian, so that the in and out states are just different by an overall phase, then these relations would also be true by CPT. So that simplifies matters. And then I'm going to introduce, just for notation, a couple of things. I'm going to write them here, and then I'm going to throw this up. A1 bar, A1. Oh, and another simplifying assumption. So this is a definition. And another assumption I'm going to stick in is that Q over P is approximately 1 in magnitude. So this is like 1 plus epsilon, very close to 1. But in fact, in the V system, there's a large phase. It's just it's pure phase. There's basically no magnitude. So I'm going to make that assumption. Oh, so I can compute two different types of asymmetries. One would be a time-dependent asymmetry, where I'm actually just putting this time-dependent difference in this ratio. And I would actually have a CP asymmetry that's a function of time. And I could try to measure that. Another thing I can do is what is called a time-integrated asymmetry. Now, you don't want to integrate the asymmetry itself. You want to integrate the widths. Okay? So the time-integrated asymmetry, so time-integrated asymmetry has, if you want, integral dt of gamma minus integral dt of gamma bar over the sum of the integrals. And I mean, those integrals are not a big deal. There's integrals of exponentials times cosines and sines. So you can do them, right? So let me show you what happens with the time-integrated asymmetry for that expression that I wrote down. And it's a little long, so I'm going to try to write it fast. Well, you know what? I already made this assumption that this is 0, so let me keep this one and just go to the shorter one there. The imaginary part of rho Q over P minus rho bar P over Q divided by a little messy stuff. So that looks short but kind of useless. And the reason it's kind of useless is that we don't know much about these quantities, and we have to explore what those are. And if we try to do this in general, these rows are ratios of some amplitudes that require understanding some strong interactions to get an answer. And one of the things that happens, which is very nice, is that this simplifies, and a lot of that uncertainty from the strong interactions goes away if you take for the final state a CP eigenstate. So for example, say the final state is something like a pi plus pi minus state. So the CP conjugate of that is pi plus pi minus. And the most famous of that has a J psi with a K short. And it's not an exact CP eigenstate because the K short is not an eigenstate of CP, but it's almost an eigenstate. It's off by epsilon. So J psi K short is a very famous case. So let's see what happens. If I do this, then A2, of course, every time I had a 2, you can replace it by 1 now because it's the same state up to a sign. So A2 becomes A1, and A2 bar becomes A1 bar. And the plus and the minus depends on whether it's a CP even or odd final state eigenstate. An important point then is that rho bar becomes 1 over rho. Because if you see those ratios, then the way they were defined, one becomes the inverse of the other. And of course, if this is the inverse of rho, there's another interesting observation. There's also the observation from this assumption that I made there, that A1 is equal to A2 bar, that kind of follows from CPT, for example. You can also show then that rho bar has the same magnitude as 1 over rho from this equation, which means that rho squared has magnitude 1, which is that says that rho has magnitude 1. So rho becomes a pure phase in this case. And if it is a pure phase, it's likely that it is something you can compute, because it's going to be given only by phases in the CKM matrix. And we'll see that that's what happens. But now that's fantastic, because Q over P, we'll also see it's just computed in terms of phases in the CKM matrix. And this whole thing has to do with CKM matrix phases and nothing to do with strong interactions. And it's the cleanest way to measure anything in the CKM system. So that's why this is worth understanding. Okay, now with this understanding here, you also see some simplifications. For example, since this is a pure phase, this quantity is just a complex conjugate of that. I mean, this is the inverse of that, and because a pure phase is the inverse. So this just doubles this imaginary quantity. On the other hand, this is purely real, so this thing goes away. So Q over P is a phase, but I haven't explained why, and I want to come to that. Okay? That you have to take for at face value and in trust for now. So here's what happens. You get delta m over gamma, the 1/2 times 2 here plus that term combined into 1 plus delta m over gamma square. And then you have this thing, which is imaginary part of rho times q over p. And although I haven't shown you this factor in front, which just depends on things you can measure, like delta m and gamma, actually this combination is very directly measurable. It's what's called the mixing fraction of the B0 and B0 bar. It was actually the first quantity that was ever measured in the B0 system, in the B0 B0 bar system, indicating oscillations. So this is something you can measure very, very accurately. Now you can predict the asymmetry. You can predict the asymmetry in terms of this quantity. So what is rho? The point I said is that rho is a pure phase. Let me do a simple case. Let me take for psi d plus d minus. It's an interesting case because you see it's a CP eigenstate, and I'll show you how it satisfies that condition that rho is 1 and that those amplitudes are equal. A1 is equal to A2 bar and so on. And then I'll show you how it fails to satisfy it by a small correction, which is important so you can understand what the physics is that's happening here. So how can the B, here's a picture that I like to draw. Here's a B0 as an anti-B quark and a D quark. It can decay by emitting a W, of course. And in doing so, it turns into a charm quark. And then the charm quark and the D quark is what you would call a D minus state. And of course, the other hand here produces a C and a D, which I can call a D plus state. And if you want to do the B0 bar case, you just reverse all of the arrows. So let's do that. So this is an anti-D with a B quark. Now this is charm, and this becomes a D plus. So it's a different state. But of course, this state becomes a D minus because it's an anti-charm and a D quark. So it's the same final state, even though in detail they seem to come out from different places. And so we can use this type of relation. So, and you see, as far as the strong interactions are concerned, these diagrams look identical. Right? The strong interactions are invariant under charge conjugation. So the fact that you change the particles for the antiparticles is something that the strong interactions don't care about. So the real difference in the amplitude here, this is what we would call A1. This amplitude has some strong interaction crap that I'm not going to write down. And then it has something that does distinguish between the two diagrams, these CKM factors at these two vertices. So the first factor here is VCV star, because a charm turning into V. And then here a D turning into charm is VCD. And then this other quantity here, which is what you would call A1 bar, has, well, the same garbage from strong interactions. But now, since the arrows were reversed, you get VCV over VCD star. And so you can see that rho, which is defined as A1 bar over A1. Where is it? Wherever. There, A1 bar over A1 is then VCD star over VCV star VCD. And it's a pure phase given by the CKM. And so I said before that that type of assumption holds if the final states are strong interaction eigenstates, and then it's just CPT. Well, these are not strong interaction eigenstates because a D plus D minus system could state, a state composed of a D plus and a D minus can evolve by strong interactions into a D0 bar. You have the same quantum numbers. But what actually produces that type of identity here is the fact that there's only these two diagrams, one for each, and then the two amplitudes are related. Okay. So to finish this thing, to get the whole thing put together, I have to tell you something about Q over P. So let me do that, although, well, I'm going to have to juggle the board up and down. There. So this is actually just doing a little bit more diagrams. It's kind of fun because you just look at diagrams and find where the faces are. We want to go back and compute Q and P, and those are, of course, just like epsilon, something that you compute from the Hamiltonian of the system, of this 2x2 system. So you remember we had an expression that said 1 plus epsilon over 1 minus epsilon is given in terms of M12 and 1 naught. Now you rewrite this whole thing in terms of P and Q. So for example, P over Q, which is 1 plus epsilon, is M12 minus I gamma 12 over 2 divided by delta M minus I delta gamma over 2. And there's a complex conjugate version of that. Now, let's go look at what is this term that appears here. And for that, I have to look at what we've been looking at this week, this kind of box diagrams. And let me have, for example, here the V0 bar, and here the V0. So this would be a V quark turning into a D quark. This would be an anti-D turning into an anti-V. And here you have U, C, and T again. And here's the interesting thing that happens in the B system that doesn't happen in the K system. If you look at this, in the kaon system, remember we had contributions to this diagram where there was the two tops were contributing, a charm quark and a top quark, or both charm quarks. The up quark was totally negligible for the imaginary part of this of M12. And all of the contributions were of the same order. In the B system case, the top quark dominates, and you can see that right away. If you just write down like we did yesterday, there's a sum of VQB, VQ, D star, and another one, Q prime, B, Q prime, D star, of a function of these quarks, MQ and MQ prime, where Q and Q prime run over U, C, and T. But if you remember these guys, you probably don't, these are the three elements, the three sides of the fat triangle, one of the fat triangles that we looked at. So fat triangle, meaning the three sides are of the same order of magnitude. And you can check that directly. VTV is order 1, but VTD is order epsilon cubed. VCB is order epsilon squared, VCD is order epsilon, so again, that's epsilon cubed and so on. Well, you see, three terms are of the same order of magnitude, and this roughly goes like the square of the masses. MT to the fourth surely beats M charm square MT square, or M charm to the fourth, and so on. So by large, the dominant contribution is just from the top quark, and there's a single contribution. You can neglect the others. There's another thing I can say while we're at it. Earlier on, I said, oh, here it is. I said, oh, delta gamma is actually much smaller than gamma in this system. So gamma, remember, has the diagonal contribution. The B0 goes to B0, for example. And so any number of states that can go on shell because the intermediate states can have the same kind of numbers of the V0 itself. But for the off-diagonal transition, this is dominated by the top quark, but gamma, remember, you only can have on-shell states. Right? So the dominant piece is coming from something that you cannot have in the on-shell case. And so you can, at the very least, see from this that delta gamma is much more than M. But you can also see that delta gamma is much more than gamma. So that's where that comes from. So by the same token, gamma 1, 2, which is that piece here, is much more than M1, 2 because there's no, for top and charm, there's no on-shell state here. And those are the dominant contributions. So we conclude, well, from all of that, we conclude that we only care about M1, 2, and that M1, 2 actually is proportional to VTV, VTD star square. All of that argument was just to show that. And if you want, you can actually push this a little farther and repeat what we did yesterday for epsilon and write a formula that gives you M1, 2 in terms of all of the parameters of the standard model. This integral that we introduced yesterday, you would use the same one, and G Fermi and all of that. And then a matrix element of the 4-quark operator. Okay. Now, since gamma 1, 2 is negligible, you can see that P over Q is M1, 2 over delta M, and then it's also equal, remember, to 1/2 delta M minus I delta gamma over 2 over the complex conjugate. So you see that if the complex conjugate is negligible, then delta M, or actually half delta M, has the same magnitude as M1, 2. So, so that means that P over Q, which is 2M1, 2 over delta M, is the same as, well, you can write it's delta M over M1 over 2M1, 2 star is just M1, 2 over the magnitude of M1, 2, which is the same, using that, as VTV, VTD star over its complex conjugate. So now let's put everything together. The asymmetry A involves, since the formula is given back there somewhere, well, if we write it, since delta M over gamma over 1 plus delta M over gamma square, then the imaginary part of the inverse of this, which is VTV star VTV over VTV VTD star, times the rho, which is hiding somewhere there, VCV VCD star. And if you did the exercise that I suggested in the first lecture, where you try to look at the CKM elements and find out how to write the angles alpha, beta, gamma in terms of ratios, just bases of them, you'd find that this thing, this imaginary part, this whole thing is e to the I2 beta. So the imaginary part is sine 2 beta. So you can measure this thing, this prefactor. If you measure the asymmetry, you measure directly sine 2 beta with any hadronic uncertainties. Side remark, to finish this up. Yep. Well, you can't ignore the you can completely ignore the gammas in practice because the things do decay, of course. But for the purpose of mixing, particularly since delta gamma is negligible, gamma 1, 2 is negligible, yeah, we could have pretended that there's no gammas. And of course, for asymmetries, the overall factor of e to the minus gamma then just falls away. So we kind of did that here, right? When we set this up, I said delta gamma is negligible. I just erased it. And then the gamma became an overall factor of both f plus and f minus, e to the minus gamma over t. And that tells you that that is going to just cancel out of all of these ratios. So in that sense, yeah, I could have ignored it, but only kind of a posteriori. Okay, so very quick remark. I did this way partly because it's historically interesting and because it's kind of very clean. But there's a cleaner or simpler thing that we learned, kind of a little bit of a posteriori. Imagine now that I do the time-dependent case. Meaning I don't do this integral. So remember, this factor of delta m over gamma just came from doing all of these integrals. So let's do this thing again. I'm not going to do it. I'm just going to give you the answer. When we start with this amplitude, f plus a1 plus t over p, f minus a1 bar, and so on. And keep the time dependence. And use, of course, the fact that for this particular case, f plus is really a cosine and f minus is I times a sine. And do the algebra. And if you do the algebra for this case, and you should do it, it's very simple, you get the following expression. Sine delta mt, imaginary part of rho q over p. That's it. That's the whole expression. Of course, imaginary part of rho q over p in this case was just sine 2 beta. Which is fantastic because if you can actually measure this time evolution, which is harder than measuring an integrated quantity, but if you can measure this, you can extract these just from looking at the amplitude. Okay. And I have one more comment, and then I'll switch gears for at least 20 minutes. So I said that this thing actually is only an approximation. In some cases, the approximation is better than in others. But the fact that, where are the diagrams? That only these two diagrams contribute is actually not exactly the right story. And that's because you can write other diagrams that contribute that have different dependence on these angles. So a typical example of that is called a penguin. I'm going to write it here so you can see the contrast. So basically, we want a B quark. Notice that the final state here doesn't have charm quantum numbers or D quantum numbers. So if I can take the, here's the W. Here's my usual UCT. I'm not going to explicitly write it down. I'm going to meet a gluon here. And if I turn this B quark into a D quark, then the final state has a D quark and an anti-D quark. And if the gluon produces a charm and an anti-charm, you can see that I can make this into a D plus and that into a D minus. But now the dependence on angles is going to be different. And it's the fact that this operator is a different operator than the first one, and it can have both different strong phases and different dependence on CKMs that invalidates the exact result here. But the result is corrected just a little bit because this is a small correction. It's a loop correction. So you can estimate those and see to what extent you can trust this result. Things are a lot better when you do J psi k short because the corresponding penguin is incredibly suppressed. And so the answer is known to be very good to about 1% or so. the diagram that, never mind. Okay. So I want to spend a little time, I would really wanted to spend a little time on effective field theory, and obviously I can never manage my time, as you can tell. But I needed to tell you a few things that justify some of the things that we did yesterday. And there's a bigger story in effective field theory that I think is important to be told. And you're going to be hearing a lot of stuff about effective field theory in other contexts in these lectures, in particular soft-called linear effective theory. So let me say a few things about effective field theory in the context of weak interactions. So there's a few things that effective field theories are designed to address. And there's some problems that we haven't even mentioned, and some that we did mention, but we just kind of squirt around. Some of the problems we did mention were things yesterday, for example, when we approximated a diagram like this by a kind of a single contact operator with 4 fermions coming out. It was not very clear what you do with these and when you have gluons, for example, connecting the inside to the outside. Why? Because if this operator is just a contact interaction like that, how do I represent the gluon coming from the inside? Now, the gluons that are just acting on the outside, you think, well, that's okay. That's the strong interactions in which I'm evaluating this matrix element. But the ones that are kind of connecting in to out, it's not very clear. And maybe even the ones that are just completely inside the diagram. How about a gluon going from one internal core to the other internal core? So what do you do with that? That was one question that we didn't know how to address. There's another question, which is kind of very interesting, which is if I start thinking about introducing a theory of strong interactions like UCSD into the picture, and evaluating these matrix elements in the context of that strong interactions, when I have a top core going around the loop, what do I use for alpha strong? Is alpha strong evaluated at the top scale, or is it evaluated at the kaon scale? And do I care? Well, alpha strong, I'm not going to try to evaluate alpha strong at the kaon scale because it's large. Let's say at 1 GeV, it's maybe a half or something like that. And at the top scale, is less than a tenth. So it's a factor of 5 uncertainty. So if you don't take care of that, something's going to go bad. And there's a related problem, of course, that I've been kind of hiding it from you. When you do this calculation, this function f, in fact, involves things like logarithms of ratios of these masses. So in particular, you can write the logarithms as logarithms of the mass over some renormalization scale. And these logarithms can be very large. And so what do you do with that? How do you handle that? It's actually, these questions are, of course, all related to each other. And so alpha is of mu what scale? And what about large logs? And in fact, effective theories were developed to deal with the problem more generally of multiple scales. So one thing that could have bothered you here is that we expanded this function in powers, at least for the old gym, and we said it had a Taylor expansion. But what if it didn't have a Taylor expansion? What if this thing diverges when one of the small masses go to 0? Or another way to put it, which is the troublesome thing that I want to avoid, is how do I know that this thing doesn't diverge when the W mass goes to infinity? So there has to be some sort of organization that allows me to understand what's going on here, so that the calculation is done in a way that large masses, let me put it this way. The calculation is done in such a way that I can control the appearance of multiple scales, either by explicit factors, which then allow me to see what terms are important and which are negligible by explicit powers of the scale, or the only thing around that is if you have logs of the different scales, in which case I already mentioned them, and I'm supposed to be able to handle them with effective theories. So this is what I'm trying to do. I don't know if I actually made sense, but that's the idea. And before you can really talk about effective field theories for weak interactions, you have to understand a more basic idea, which is contained in what's called the Appelquist-Carrot-Sonnet theorem. It's called a theorem. I don't know if that it is a theorem, but that's what it's called. I'm not a mathematician, so I don't like to call anything a theorem because I don't know how to prove things. But I can tell you what the content of this and why it makes sense. So here's the idea. You take a Lagrangian for some field theory, and this field theory contains some fields that are, say, one field that is heavy and other fields that are light. So there's a Lagrangian for the light field, a Lagrangian for the heavy field. I'm going to take it to be a real scalar. I don't know why, because I'm not going to do anything really explicitly. And then some sort of coupling of the heavy to the light. So phi times L coupling. It doesn't have to be linear, but that's kind of the simpler thing. So these functions, L light and L coupling, are functions of the light fields only. And there might be a whole bunch of coupling constants. Some coupling constants are just coupling the light degrees of freedom to themselves. And other coupling constants that appear in this other term involve, of course, the heavier field. And what we want to consider is some process where you have particles come in and out, where all of these particles have momenta, P1, P2, all the way to Pn. Maybe some are going in, some are going out. Where the momenta of all of these particles is of the order of the light masses. So that tells you already that none of these particles is one of the external. None of these external particles is the heavy particle, because that one has to have momenta. If it's going to be on shell, if it's an actual particle, that has to be at least of order m. Think of the zeroth component of momentum. That's the energy. At the very least, is the large mass. So we're assuming that this light mass is much smaller than m, that the heavy mass. Now, there's of course two types of contributions. If you open this up and look at these interactions inside, there's some contributions to this amplitude where all of the interactions are just light particles scattering or hitting light particles interacting with themselves. But there's also the possibility that there's some interactions in this black box that involve the heavy fields. And the question is, how do I deal with that? And intuitively, you think the heavy particles shouldn't play any role whatsoever, because there's no way to produce them on shell, to get them excited so that they would, 'cause, produce any role. Now, I'll correct that statement momentarily, but let me tell you kind of the statement of the theorem. The theorem is you can compute this Green's function. Let me call this Green's function Gn, which depends on all of these momenta and all the coupling constants. Then we call them G, just as I said, the coupling constants of this light Lagrangian. So I'm going to put them in here so you can keep track of them. You can compute those in terms of another Lagrangian. Some Lagrangian then called the effective Lagrangian. And actually this effective Lagrangian is exactly the same as the Lagrangian for the light particles, except that the couplings take a different value. I might have to modify the couplings. And I'll explain that a little bit better in a second. But in terms of that, you can, there's a factor, I'm going to call it Gn2. Let me call it G tilde. And then there's these G stars. So in a way, this is a factorization. Well, the factor in front, this is like a wave function normalization type factor, may depend on the mass m, on the big mass m. But because it is a factor in front, it doesn't change any of the analytic properties of this function, which is what matters to us, in physics. And these quantities G star are actually functions of the original G's and m. And of course, they might depend on the renormalization scale mu, so I'll put it in there, and of the masses of the light particles too. So one thing that I should explain is it's assumed in the theorem that you write down the most general Lagrangian consistent, that is renormalizable, consistent with whatever symmetries you have in the Lagrangian. It might be the case that the number of coupling constants here differ. And I'll give you an example momentarily. But physically, this kind of makes sense. The interactions are taking place among these light particles. So think about electrons scattering on electrons. The fact that there's a Z boson at 90 GeV shouldn't much matter if the interactions are at the atomic scale, for example, right? Or at a 1 GeV scale. But on the other hand, if you think of the electromagnetic coupling, there's going to be some sort of loop correction to it, which at some high order involves a Z boson running around some loop. And so implicitly, in that electromagnetic coupling at some high order, there's a correction that involves the Z mass. So I can just say, well, forget about the Z. And there's a new coupling, which I call the electromagnetic coupling star, which I could write if I wanted in terms of the original coupling of the theory, which included the Z. But I don't have to if I don't want to. I can just compute everything as if the Z didn't exist. And that's great. If nature was not, if mathematics were not like that, nature would not be accessible to us. So you wouldn't be able to understand how atomic physics works if you didn't already understand that the Higgs exists, or maybe even that there's grand unified fields. And it would never have made any progress in physics. So the whole notion of effective field theory is kind of fundamental to the ability of doing science and particular particle physics. Okay. So one interesting example of this, by the way, is grand unification. And this is part of where this whole story was developed. In grand unified theories, maybe I'll do it here. In grand unified theories, of course, we don't much care about the fact that there's particles that are incredibly heavy. If you want to describe things like BB bar mixing or Higgs to 2 gamma. or electroweak precision measurements for that matter. But if you start, if you write down the grand unified Lagrangian, of course it has light degrees of freedom, heavy degrees of freedom, and some very specific couplings among the light degrees of freedom. And according to this theorem, you look at the light Lagrangian in the absence of all of the heavy degrees of freedom, and you write down the most general thing that you can write down. And you find that in the unified theory, I should do it here because I still have space. In the unified theory, there was only one coupling constant, G5 for SU5, if it is unification. I should call it G GOT. The unified coupling constant for the gauge interactions. But in the theory at very low masses or low momenta, there's actually 3 possible coupling constants you can write down because the theory has SU3 cross SU2 cross U1 invariance. And in fact, these 3 couplings are what I call G star in here. All 3 of them are actually just given in terms of G GOT and the mass of the heavy particle or particles, so the unification scale over mu. So of course it turns out that these 3 things look to be different, but the distinction arises because of the presence of it's really one single coupling constant you have, but the distinction at low energies is arising from the fact that in loops you can get these heavy particles. I'm actually going to try to explain that because if nothing else you can get that home with you. Here's a very simple process. E plus E minus to me plus me minus. What I want to do is I want to explain this in a grand unified theory. And I don't want to use effective Lagrangians. I want to see where the difference between this process and a process involving quarks comes from. In a grand unified theory, if I write this diagram and a corresponding one taking U quarks to D quarks, I would have exactly the same couplings in these vertices, just G GOT. Okay? So how come the electromagnetic coupling is different from the QCD coupling? Well, let's look at the corrections to this. I'm not going to do all of the corrections to this, but I'm going to do some generic correction involving here some GOT heavy particles. Okay. So again, these are photons, and these are some GOT heavy particles. There's a lot of particles that can run in that loop, and I don't want to be specific. Now, if you compute this loop, notice that this thing looks like there's derivative couplings here and 2 propagators, so it looks like quadratically divergent, but the gauge invariant makes it logarithmically divergent. If you renormalize it, this diagram is going to produce a log of m GOT over mu. And the coefficient will depend crucially on this thing being a photon versus in the other graph having gluons. And there's of course other diagrams, but let me just concentrate on that. And if I want, well, never mind. So suppose that I actually resum this diagram by using the usual geometric sum of sum of bubbles. So this thing becomes, I'm going to be very sketchy here. The self-energy diagram here I'm going to call pi of q square, or q square pi of q square. It's just pi of q square that I'm going to need. So that, roughly speaking, what happens is your propagator, instead of 1 over q squared for the photon, becomes 1 over q squared plus pi. Fine. And of course, there's a factor of G5 square from the two vertices at the electron and the muon. There's, of course, other factors of G5 here, but those are included in pi. So roughly speaking, this photon is coupling with a coupling constant which looks like G5 square over 1 plus, and really if I'm a little bit more careful, it will be a G5 square over 4 pi square times log of m God over mu, and times 1 over q square. I'm hiding a little bit of the story in the interest of time, but the coefficient here will actually depend on whether this is a photon or a gluon or whatnot. And you see that effectively this whole term is E squared. And the fact that this coefficient changes from photons to gluons means that for gluons you get something else, and we'll call that G3 square, and so on. And it would be impossible to try to do this diagram by diagram and keep track of it, and the Appel-Quist-Carrazzone theorem says you don't have to. Okay? You just call them three different things, and if at some point you want to relate them to the underlying theory, you can do that. And the important thing is that you don't have to go process by process. It's universal. And that's contained in the way I wrote that formula. It's the same couplings that appear in any Green's function. Okay. So of course, this is not the whole story, because in fact, you cannot ignore completely the effects of these super heavy particles. You can have some processes in which the super heavy particle plays a role. In other words, without the super heavy particle, you wouldn't have that process occur at all in this Lagrangian L light. And an example of that, but there's proton decay, right, which doesn't happen in L light, but it does happen in the grand unified theory. You can certainly write down examples of, I don't know. Well, I'm not going to write down anything explicit. QU, QE type couplings, where the E is coming from the lepton doublet. No, actually, I have that thing. Never mind. You can have that, which is not in L light, and of course, this is an M God particle. And what do you do in order to account for that? Well, what you do in order to account for that is you say, well, I can actually change my effective Lagrangian by supplementing that with new terms, which are, however, they cannot be renormalizable terms in a Lagrangian, because I already said that all the renormalizable terms are here. So this type of effect must be accounted for by some non-renormalizable type term in the Lagrangian. And in this case, you can see it's basically 1 over m God square times, again, some 4 fermion operator, QQUE type operator. Now, the same thing happens, of course, in weak interactions. And where we supplement the Lagrangian by things like 1 over mw square, and then things like S bar D, S bar left gamma mu D, S bar left gamma mu D, for example, which we did see in the previous lecture. So I'm going to take a couple of extra minutes for the lecture. I have a couple left, but I'm going to go over a couple of minutes to show you one of the interesting aspects of this, and how you deal with this type of interactions, and how dealing with them properly allows you to take care of these logarithms and so on. How much can I actually do? Okay. I don't think I'm going to tell you about the logarithm resummation and so on. We'll have to leave that for another day. But I want to show you how these things are consistently treated and why they actually work. I didn't actually give you a proof of the Appel-Quist-Carlsson theorem, but you can kind of see how it goes. Imagine taking any massive particle inside the diagram, and imagine taking the mass of that particle to infinity. What you have to prove is that either it appears as inverse powers of that heavy mass, so it goes to 0, the effect, or it grows but only logarithmically. And if it grows logarithmically, then you have to show that those logarithms can be absorbed into redefinitions of the couplings, and that's what is done in that theorem. And it's not easy to prove, so I'm not going to try to do that. But I'm going to settle for something else. I'm going to settle with trying to understand the addition of this extra delta L term, which I'm going to do with a 4-fermion interaction like that. And I'm going to be sketchy. I'm going to say here, we have a theory, maybe it's the weak interactions, maybe it's the grand unified theory, with 4 fermions like that. And this is a heavy particle. So it's actually useful to think of this as a W and this as quarks. And what I want to do is I want to say, well, look, the effective theory tells me replace this by 1 over m squared times a diagram like this, a 4-fermion operator. And that is trivial, right? That you can check. If you don't understand what I'm talking about, you should have checked this. You take the propagator, set the momentum to 0, you get that. Actually, we did it yesterday in class. The non-trivial thing is the following. How about this diagram? That's a gluon. That's a massless particle. It's part of the light degrees of freedom. Is this, let me say this is equal to that in some approximation where the approximation says corrections that are smaller than these by order of the external momentum of this over this heavy mass. That's what we were assuming after all. Right. But how about this? Well, this equation actually makes absolutely no sense. The left-hand side is a finite Feynman integral. Do the power counting. There's 2, 4, 5, 6 powers of momentum in the denominator. Whereas the right-hand side has 4 powers. So it's logarithmically divergent. So we have infinity equal not infinity. So, so we like to see that these guys are equal. So we can say that even in the presence of strong interactions, for example, replacing these by that is a valid statement. So here's what well, let me show you how that actually happens to be correct. Well, they're not exactly the same, but what we really want to show is that the momentum dependence is equal. Now, even in the insertion of this operator, right? So think of this with an insertion of the operator O. Well, O on this side, and the full thing on that side. But not exactly equal. It's up to corrections. So here's what I'm going to do. I'm going to take a derivative with respect to external momentum on both sides of the equation. When you do that, a derivative with respect to external momentum, imagine this momentum is rooted this way. It goes to this propagator. The derivative with respect to momentum of 1 over p squared gives you p over p2. Gives you something which is cubic now in power counting. So it makes this even more convergent than before. You can think of this as inserting an insertion of a momentum there with 2 propagators. That's what this is. It makes this thing convergent. And now that these 2 sides are convergent, you can try to prove that they're equal. And it's actually very easy to prove that they're equal in the limit of large mass, because you can basically take the limit of large mass inside the integral, they're uniformly convergent, and show that they converge to the same limit. And you can do this with taking the with respect to any external momentum and find that this is true, or the light masses. So these things are equal once you take one derivative. So, so they differ only by something which vanishes as soon as you take a derivative with respect to external momenta or light masses. which means it's a constant. It's a total constant. It doesn't depend on momentum. Of course, it has the same spin or indices as these things, so it really looks like the operator we started with, just a constant times 4 fermions. And of course, there's an explicit factor of m squared I can always put in front of my definition of the constant. And so the interesting thing, you can see that this constant is order G strong square by construction. Had I renormalized this theory, had I worked with a regulator, instead of infinity, this would be order 1 over epsilon. And this constant, to make this thing make sense, would also be order 1 over epsilon to cancel the infinity so that this side is finite. So once you renormalize the theory, this is still true with some finite constant and some renormalized graph here. And combining these two, I can write now this very nice equation, which is the last thing I'm going to write on the board before I just give you some last remarks. So I combine the two equations. There's 1 over m squared. There's an extra term here, which is c times the graph with the loop. But that's order g strong to the 4th, which I haven't considered as higher order. But you can actually prove that this actually can be extended to all orders in the loop expansion. So you see that what's happening is that the graph dressed with all of the gluons that you want is equal to dressing the effective theory with gluons, provided you put a constant in front to account for the difference. And that constant in front doesn't depend on momentum, of course, it is a constant, doesn't depend on the light masses. So what can it depend on? It can depend on coupling constant, we already know that, and the heavy mass. So, where is it? So this effective Lagrangian has a constant in front of it. The constant is a function of m and g, the coupling constant, of the light coupling constant, g star in this language. And it's dimensionless, so it depends on m only through the ratio m over mu. Okay? So I'm going to stop now, but what you learn from this is this thing works. This is why it works. It works because you get the same behavior at low momentum. So you have the analytic behavior is the same of these theories. At large momentum, they don't, but we don't care about that. And the coefficient has this very simple property that only depends on the large mass to this ratio m over mu, which is amenable to understanding by using normalization group methods, which is what's usually done. And if I had another 2 lectures, I'll show you how, but I don't. So I'll stop there. Thank you very much.